Hi, everybody. It is me, Miss Adano. I am recording this here on Monday to prepare you for your sub day on Tuesday. So, welcome first off. I hope you all are having a great day. Let me go ahead and pop open the slides that I've prepared for you all here today. So, I hope you all are doing great. First off, let me go ahead and get to my Zoom slide. Okay, so as you all know, yesterday we did not get to finish our Desmos activity, but don't worry, that's what we're going to be doing here today. Recording will be up as well, so you could go back to this video and so forth. So welcome to our sub day, unit 4, day 6. It's loading for me, but we'll get us started in just a sec. All right, there we go. So if you haven't yet, feel free if you'd like to make a copy of the slides, keeping in mind that we're mostly going to be in Desmos today. Okay, so as our check-in, make sure that your sub has taken your attendance down and that you're marked present. Make sure that you also complete today's Desmos activity and you answer all the parts where you're required to answer a question so that I can mark you down for credit. Today, our opener is to think about something you're grateful for today and just hold on to that gratefulness as we go through today's lesson. So let's focus on some gratitude and then we'll move on. Okay, everyone, I'm grateful for the exercise I got this morning. My walk from the BART to school. I don't know. It really brought back memories. So I'm really grateful for that. Feel free if you'd like to share with each other what kind of gratitudes you have. Not necessary to share. There's a different way y'all are taking attendance today. So let's just roll with it. Okay, y'all. So our agenda today is actually to finish up the Desmos activity from yesterday. So let me go to yesterday's slides so that you all know the code. You're going to go back to student.desmos.com. You're going to type in this code. You're going to make sure that you're logged in and you answer all the questions as you follow along with my lesson today. So let's have a moment. Go ahead and log back in. Take about a minute, y'all, and then I'll take us back. All right, everyone, there's our minute timer. So let's jump into Desmos right here. Hey, if you didn't notice, look at the title, The Fundamental Theorem of Calculus. We are finally there, everyone. We're finally going to talk about the fundamental theorem. So what I've done, I turned off the pacing. So you are, once you log into this Desmos, you're able to kind of go through it on either at your own pace, but I do recommend that you follow along with me as we do this together. Now, one thing that you're not going to have It's the ability to get my feedback or to look at each other's answers, as we go about this. I mean, I know there's times where you enter in an answer you're able to see, so I'm hoping that's still there so you can still look at each other's answers. But here we go, y'all. We're going to be finally touching upon the fundamental theorem of calculus. The essential question that's guiding our Desmos activity today is how is the integral connected to the antiderivative? That's the essential question. Now, yesterday, I went over slide 2 and we found the area of this triangle to be 2. We talked about this one yesterday. Slide 3, we also talked about this one. We found that the area of this triangle was 4.5. And again, just a little bit of a shading in just to make sure that I am giving us a reminder. So it was all the way up to 3. There we go. There is the region that we're interested in finding. The area of 1/2 base times height is the formula for the area of a triangle. We found this to be 4.5, which is equivalent to 9 divided by 2. Next, to finally recap what we did, we left off yesterday on slide number 4. On slide number 4, I asked you all to go ahead and to find the area or to AKA calculate this integral from 0 to 4 of x dx. I provided the visual for you, and all of you got an answer of 8, and there were different ways that you all explained it. Some of you did it in direct math words, math language, and some of you did it verbally with math. So take a look at my screen here to see everyone's explanations. If you're stuck, review this. Take a look at someone else who explained it and try to help yourself out here if you're still a little stuck on this. All right, so cool. Oh, I'm sorry, we didn't leave off on this. We actually left off on slide number 5, where I showed you, okay, so we have the area from 0 to 2, we got 2. From 0 to 3, we got 9 divided by 2, aka 4.5. And then for the last one that y'all did, we got the area from 0 to 4 is 8. And I asked you, are there any patterns you notice? So we have the pattern I noticed is that the answer is always divisible by 2 in some way. Oh, okay, like 2 is divisible by 2. We have 9 divided by 2. Then we have 8, which is also divisible by 2. I see that, Gregory. We have the higher the integral, the higher the area. Of course, yeah, because as we're expanding how much area to calculate, we expect to see that the area gets larger. I love that. There is some sort of connection to the number on top. Specifically, like 2 is being equal to 2, and then we have 3 times 3, then 4 times 2. See what they're seeing here? Like 3 times 2 or whatever gives you 9. 2 times 1 gives you 2, and then we have 4 times 2 giving you the 8. So they're seeing some connection with that number on top. The number on top, y'all, does have a specific name. Let me write that down. So the number on top is called the upper limit sometimes, or the upper number of the integral. So I call it upper limit for the top number, lower limit for the bottom number. Up to y'all how you want to kind of, better express that. But upper limit is more of the formal terminology of how you say it. But that's the noticing we're getting here. Pierre is noticing that we're always getting a triangle. It's not always going to be the case, but in this case, yeah, that is a legit thing. All right, so cool. So those are just the things I'm noticing here. So I'm going to go ahead and clear this up. And I'm going to transition us to the new slide, slide number 6. So please join me. You are now in this Desmos. It is self-paced. Join me. So y'all, what is the pattern? I guess I'll stick to teacher mode. This is the pattern, everyone. So the pattern appears to be, now some of you didn't come up with an equation for the pattern, right? But some of you did notice some connections. So let's read this. The pattern appears to be that for this particular function, the area is 1/2 x squared. Let's test this out right now. Oh, but it says, but the x is being replaced by the upper integral value. There's another way you could call that upper limit value, that top number. So someone did notice that, so that's really cool. Is being replaced by the upper integral value each time. So let's test out this formula. Let's see if this is legit, y'all. So for this one, we should get 2. So 1/2, and then the x is being replaced by the upper value there, upper integral value. According to PEMDAS, we do exponents first. So 2 squared is 4 divided by 2, that is 2. That checks out. Now let's go ahead and apply the same formula, 1/2. And instead of x, we're going to put that upper limit value. In this case, it's 3. Let's remember PEMDAS. 3 times 3 is 9, divided by 2, 9/2, or 4.5. That checks out. We got 9/2. Now let's check this last one. I mean, so far it's looking pretty legit that is actually a formula for this particular function that will get us the area. 4 times 4 is 16, divided by 2 is 8. They all check out. Feel free to test this out on your own, but this pattern, 1/2 x squared. Now, where is 1/2 x squared coming from? Feel free to put this in the chat if you have an idea. Where am I getting 1/2 x squared? And how in the world is this 1/2 x squared related to the x that I have here as my function? Pause and think about this. Okay, everyone, you ready? Are you ready for the connection to the essential question? Everybody, there is a connection. What if we find the antiderivative of this thing? What is the antiderivative of the first power? Remember our antiderivative formulas, everyone? So in order to find the antiderivative of, say, x times some function, what you would have to do is you have to do this formula, which is x to the n plus 1 divided by n plus 1. And then you had your plus c at the bottom, right? Let's go ahead and find the antiderivative of x to the first power and see what it gets us. So I have to do 1 plus 1, that's x squared, and 1 plus 1 at the bottom. Well, x squared divided by 2, that is exactly the same thing as 1/2 x squared. Now, y'all see this connection? The pattern is the antiderivative of the function. Let me write that down because that is huge. The pattern slash formula is the antiderivative of the function. We're now touching upon answering that essential question. Let me remind you what that is. How is the integral connected to the antiderivative? I just now touched upon that right here, y'all. Let me let you process this, and then we're going to check out what that connection is. Exactly and precisely. Okay, everyone, let's go ahead and transition to slide number 7. There is a rule, and we're going to make some connections now. The fundamental theorem of calculus, everyone. Specifically, this is fundamental theorem part 2, actually. So let me write that down. Fundamental theorem of calculus part 2. There's actually 2 parts to the fundamental theorem. We're going to just be touching upon part 2 right now. Let's read this. And for the moment, ignore what I have down here. But let's read this. Let f, your function, be a continuous function on some interval. So from x equals a to x equals b. If capital F is any antiderivative of f, that's again on the same interval from a to b, then the definite integral, so a little bit of new vocabulary, of f from a to b is defined by this. The integral from a to b of my lowercase f dx is equal to capital F of b, so you're plugging in this upper limit value, minus capital F of a, plugging in the lower limit value. Capital F, remember y'all what that means? Capital F is any antiderivative of f. Wow. So areas under curve, everyone. Areas under curve. We're now connecting that to antiderivatives. That's kind of huge. It is kind of huge. How we read this is the integral from a to b of f of x dx. That's how you would read that, like precision. Now, how does this formula connect to what we just did right now? That's what's shown right here at the bottom. So how this formula connects, for the prior problem, remember we started at 0 and went up to some number. Let's call that some number b, and it was x dx. Now the antiderivative of x dx, and I can't see well because my thing is in the way, the antiderivative is 1/2 x squared, right y'all? The antiderivative was 1/2 x squared, aka that's the same thing as x squared divided by 2. Step 1, antiderivative, we found it. What this formula says is you now have to plug in into the antiderivative, you got to plug in that upper limit value and subtract it by the lower limit value. So we have upper limit b minus lower limit a. So I just color coded those. I subtracted because that's what the rule is telling me to do. Next says I went ahead and just plugged in. So I know that my lower limit for that last problem we just did, the one we were investigating, was 0. So a is 0. Let me make sure I show that color coding here. So a is 0, and my b is in blue. It's just b. It's whatever b is. This b was changing. It was 2, 3, 4. It was changing. So we plug in 0. Well, we have b squared divided by 2 minus 0 squared divided by 2. Well, 0 squared is 0, and 0 divided by 2 is just simply 0. So basically, this whole thing goes away. It cancels out. And what you're left over with is the formula that it is the upper limit value squared divided by 2. Basically, the antiderivative, but you plugging in whatever that upper limit value is, or that upper integral value, however you want to think of that upper limit value in phrase. So that's how this fundamental theorem of calculus part 2 connects to the investigation we were just doing yesterday and continuing today. That is impressive. Let's go ahead and take a look at how to do some more examples with this, everyone. So I'm going to clear my drawings. Let's get to it. And you know what I don't like about Desmos is that I can't pop up my steps step by step. So what I did instead is I kind of just put in a little verbal explanation of what I did. So let's apply the fundamental theorem of calculus to this example that you see right here. Example 1, finding the integral from 1 to 3 of x dx. Notice how my lower limit is not 0 no more. I'm now deciding, hey, let's find it from 1 to 3. Okay, before y'all dive into these steps, let's go ahead and figure out what this would visually look like in our graph. So let me shade in the area. So from 1 to 3. It looks like it's a trapezoid. Now, if you know the formula of a trapezoid, feel free if you want to try to calculate the area. But here's the thing, y'all. We don't want to just sit down and start calculating geometric areas of figures. We're going to simplify our lives by applying fundamental theorem of calculus part 2 so that we don't have to keep doing geometry this time. We're going to just now have this rule that'll make life easier. So here's the steps, everyone. So to find the area under this curve, the shaded region, we're going to apply FTC part 2, fundamental theorem of calculus part 2. Let me show you how I write down that shorthand way. We say FTC, and we're doing part 2. Part 1 will come up later, but part 2, let's apply this. So step 1, find the antiderivative. In calculus, we just call this with the uppercase F. My antiderivative of x, as we've seen before, is 1/2 x squared. Got it? Next, the antiderivative, the FTC theorem part 2 tells us that we need to plug in the upper limit value into the antiderivative, subtract it, and plug in the lower limit value. Notice how I did that here. I plugged in my 3 first, I subtracted, and then I plugged in my 1, my lower limit value. What comes next is you simplify. Don't forget your PEMDAS. So you got to do 3 squared first. That's 9. And we have times 1/2. That's just 9/2. 1 squared is 1 times 1/2 is 1/2. 9/2 minus 1/2 is just 8/2, which is equal to 4. And then I put simplify. That's our answer, everyone. That's the area. You could go ahead and verify this work by finding the area of this region, but you'll see that your answer is 4, and you see that this theorem is legitimate. It's real, y'all. It's crazy. Okay, let me let you go ahead and take a look at these steps. And if questions do come up, once it's time for you to enter in some responses, feel free to jot in your questions, and that way I could get back to those when we meet up again on Thursday. Okay, everyone. So feel free to look back on the slide if you still need more support. But now, let's go ahead and you try. You're going to try this out now. Let's see where you're at. So right now, I'm going to wait for responses. Actually, I can't see them yet. Y'all are still working on this, but you're going to find the integral of this here thing, and you're going to sketch the corresponding area in the graph. Let me look at the student mode. There we go. You're going to find the area. You're going to enter in your answer with your work, and I want you to sketch in using the sketch tool because you could draw here. I want you to sketch what that area is. So I need you to also understand what is the visual connection with what you're being asked to do here with the integral. Go ahead and take the next minute or 2 to do this part. I'll pause this for a minute and then we'll come back. I'm excited to see everyone's work, by the way. Let's be back in a minute. Take 2 minutes if you need it, by the way. Again, this is, you can keep going back and forth, but I do want encourage you to follow along with me. Because otherwise, if you don't, it might be confusing, a confusing mess. Welcome back, everyone. So that was about a minute. Again, feel free to enter in your response if you want more time on this, because of course, when I'm done recording this, there's gonna be a little bit extra time for you to go back and to adjust your response. Now, slide number 10. I want you to try now this one. So take a look, y'all. You're going to be asked to find the integral from -1 to 2 of 5x squared dx. I went ahead and also put the graph for you so that you can as well shade the region that you're being asked to find. And I need you to write out your steps. I need to see exactly your work so I can understand where everyone's at. And if you are stuck, right, I need you to write down where you're stuck at as well so we could come back and talk about it on Thursday. Let's have 1 minute or two. This part, go ahead and enter in your work. Then we're going to come in for our closing of this Desmos activity, everyone. Okay, everyone, that was about a minute. Now, I have my training for hybrid coming up, so I'm gonna go ahead and move us on. Again, feel free to take your time and to go back to this if you need more time. And I am trusting that you're able to see student responses as you're entering these in. Now, our very last slide that you want to complete is rate your understanding right now of what the fundamental theorem of calculus part 1 is. So remember, part 2. It's FTC part 2. So what is your understanding of FTC part 2? Fundamental theorem of calculus part 2 is what we're doing here. So right now, rate your understanding. I can't make any edits to my slide and add part 2 because we already started this. So rate it from 1 to 10. 1 is not well, 10 is very well. This is so going to help me understand where we need to go. So, and please tell me why, if there's a why too. Remember, your names are anonymous, so feel free. And jot down any needs that might additionally help and support you. What you're going to do next, everyone, is once you're done with this activity, right, with the sub, this is going to be your credit for today. But once you're done with this, you're going to go ahead and get started on asynchronous number 9, which is not there yet. But what it is basically is, let me just go at it now. What it is basically some Khan Academy practice on the fundamentals theorem of calculus part 2. So that is what it's going to be. Let me go ahead and add it just now. Don't worry, you guys have this already. So you'll have your practice, asynchronous number 9. It might be this one. Make sure and verify that. Okay, yes, this is correct. So take a look. I've done my homework. I did this on Sunday, but what it is basically, asynchronous number 9 is due for you all on Wednesday. There's going to be a short video. You're asked to take notes, and then you have Khan Academy practice where you're being asked to apply fundamental theorem of calculus part 2 with direct calculations. This is what it looks like, everyone. So if you click it. Now, let me give you a warning. When you see these, they're going to look a little longer, but they're basically the same thing. they're basically applying what we just did today. You know, it's loading for me, but once it loads, let me show you what to do if you're stuck. And again, this is going to be due on Wednesday, but get a start on it if you have extra time right now. See, take a look, evaluate definite integral. So let's say I'm stuck. I'm going to click here. I'm going to ignore the video part unless you want to watch it. And there we go. There's step one. Got another hint. There's step two, plugging in. Another hint, the answer. So go ahead and understand it. And if these steps don't make sense, you want to write that down for me on your asynchronous assignment or record which problem this was, and we could talk about it in class Thursday. So this is how asynchronous 9 is going to break down, and it is related to today's work that we did on the fundamental theorem of calculus, part 2. All right, everyone. Enjoy. Let me know how it goes today. Bye.